Okay, so SN2 reactions compared to SN1, remember the big difference is that we have a single step in the SN2 reaction and we have two steps in the SN1, make the carbocation and then everything react. So eliminations are going to be the same way. We're going to have our E1 mechanism where things take multiple steps to happen. We make the carbocation, we remove the neighboring hydrogen. In the E2 reaction, of course, everything's going to happen at once. So let's take a quick look at how one of those will go and see what happens. Okay, so the E2 reaction is another elimination. That's what the E stands for, where the hydrogen is removed from the neighboring carbon and the leaving group leaves all in one step, in a single step. Right, so once again, this is a concerted mechanism. So let's look at this way, right? We have a leaving group, we have a hydrogen here, we have O minus. So this type of reactant is going to be one that you're going to want to recognize, right? These are alkoxides, negatively charged oxygens. And alkoxides in general are good bases and not great nucleophiles, right? We talked before about how oxygen is not a great is a very poor nucleophile when it's neutral. It turns out that even when it's negative, it kind of prefers to do Bronsted-Lowry acid-base reactions. And so if you have something like methoxide, right, what it's going to do is instead of reacting with the carbon where the bromine is attached, it's going to take this hydrogen away. We're going to form a pi bond and we're going to kick out the leaving group all in a single go. Right, so you're going to get a double bond that looks like this. So E2 mechanisms are like this, right, where all three arrows occur simultaneously. Right, this is a concerted mechanism. So every E2 mechanism will always have all three of these arrows, right? You'll have your base going to hydrogen, right, and you're going to make your conjugate acid, CH3OH. Right? You're going to make the pi bond. So that hydrogen, as we remove that hydrogen, we would make a negative charge in this carbon, but instead of just hanging out negative charge on carbon, it's going to basically do resonance and convert that lone pair into a pi bond. And then we're going to kick out the leaving group. The bromine is going to leave as well. So the other thing we get here is we get a sodium plus Br minus. If you balance your equation, right? This is the only thing that we're really too concerned about because this is the organic product. You don't have to draw out the completely balanced products every time. All we really care about is the organic product. So we're going to make alkenes this way by using a strong base. E2 reactions require a strong base. This is usually going to be an alkoxide, although we'll talk about a couple of other strong bases. Alkoxide or others, right? We'll talk about other strong bases here in a little bit. But for the most part, we're going to worry about alkoxides for now, right? Those are our strong bases. So E2 reactions require a strong base. This is very much like SN2 reactions, right? SN2 reactions require a good nucleophile because everything has to come together and be reactive at the same time, right? We can't make a carbocation and then wait for something else to come in and decide to react with that carbocation. We need to have a strong base. We need to have a good leaving group all at the same time so that both things can happen at once, right? We can have the strong base come take the hydrogen away, and we can have the leaving group leave at the same time, leaving behind this pi bond, right? So E2 reactions versus E1 reactions, it turns out that the difference between these isn't so much carbocations. The difference between these is more about, do you have a good base? That's going to favor E2 versus a poor base. That's going to favor E1. Right? And so we need to talk about what makes a good base versus what makes a poor base, right? Good bases are going to be alkoxides. These are any R group with a negatively charged oxygen on it, right? So those are going to be good bases. And then we have a couple of kind of special bases that we're going to come back and use again. So I'm going to list those here. Sodium amide, which is NaNH2, Na plus, nitrogen minus. So a negatively charged nitrogen, right? Negatively charged nitrogen is always a good thing. LDA is a shorthand for lithium diisopropyl amide. So this is another negatively charged nitrogen with a positively charged lithium there. So you have sodium amide, right? Negative charged nitrogen. You have lithium diisopropyl amide. These R groups are isopropyl groups. You get the same thing here. So negatively charged nitrogens are also going to be good bases. And the last one that I'm going to put on here is sodium hydride. Na plus and H minus. Right, H minus is a nice strong base because the conjugate acid of H minus is H2, right? And H2 is very, very stable. These three are almost all, these are very strong bases, right? These are a whole nother step above alkoxides, right? You only use these if you really have to pull out the super strong reactive stuff. We're going to use these again when we get to the alkynes chapter. So I'm going to group these three together here. These three are worth memorizing, just kind of keeping them together. They can kind of be used interchangeably, so you can use any one of them anytime you want. But also alkoxides are another good indicator that you've got an E2 reaction going on. The poor bases in E1, these are a lot of the same things that we saw in SN1 reactions. So these are mostly going to be alcohols. So things like methanol and water, right? Ethanol, right? Alcohols like that. This generally going to be your choice for poor bases in E1 reactions. Okay? So we have alcohols, alkoxides. Looking at the conditions, right? Strong bases are generally going to be things that are charged, so negatively charged oxygens, negatively charged nitrogens, and all of that kind of stuff. The last thing that we have to talk about is what happens if we are trying to determine the difference between E2 mechanisms and SN2 mechanisms, elimination versus substitution. Okay? So we said with E1 and SN1 that it's kind of hard to tell the difference between them, right? We have to look at heat versus no heat and that kind of stuff. E2 and SN2 is a little bit more cut and dried. You have the list of bases that I gave you on the last slide. If you see those bases, it's generally true that E2 is going to be favored, right? Remember though that you also have to have a hydrogen at that neighboring carbon, right? If there's no hydrogen at the neighboring carbon, it doesn't matter how strong your base is because there's nothing for it to react with. So you have to look at your substrate and make sure that you can remove a hydrogen from the neighboring position, right? So a common example of this is if you use benzyl bromide. Let's do ethoxide, right? So you have a negatively charged oxygen here. So initially you would think E2, right? But in this case, you have our leaving group is attached to this carbon here, and the neighboring carbon has no hydrogens on it. No hydrogens on neighboring carbon. And so it cannot do no E2, so it has to do an SN2 process then. Right? That comes in, reacts with that carbon, the bromine leaves, and you get your substitution reaction. Okay. So in this case, you would get, therefore, you get SN2 reaction. So sometimes you won't be able to do eliminations because there are no neighboring hydrogens to take away. The other times you're going to look for good base versus good nucleophile. Right? And so we have rules for both of these, right? Generally, we've been seeing things like O minus, N minus tend to be good bases. Good nucleophiles tend to be things like sulfur, um, nitrogen. Neutral nitrogen tends to be a good nucleophile, although nitrogen is an okay base too. Nitrogen is kind of in this in-between area here. Um, And then things like iodine, I minus is a very poor base, but a very good nucleophile. Br minus is a very poor base, but a very good nucleophile. Um, as we go down the periodic table, further down the periodic table, we tend to get to better and better nucleophiles, right? So things like phosphorus, that has a lone pair, would be a good nucleophile, but not a very good base. Right? So O minus and N minus tend to be good. Where's my arrow here? O minus, N minus tend to be good bases. Other things tend to be good nucleophiles. Okay, so that's kind of just a general rule of thumb for these kinds of things. Differentiating between E2, SN2, E1, E2, E1, SN1, there's a lot of things to consider, but really it boils down to what are the reagents over the arrow, right? If you have a poor nucleophile or a poor base, then you're looking at E1 or SN1. If you have a good nucleophile or a good base, then you're looking at E2 or SN2. And then once you figure that out, you have to go a little bit further into it and say, okay, is this a good base or a good nucleophile? Is there heat? Is there not heat? And use the kind of signposts that we talked about in this video for to make that final determination between elimination and substitution. All right, so that is our introduction to eliminations. We're going to do some examples of eliminations when we get to alcohols, which is going to be the next group of video lectures that you're going to see.